So we wanted to spend a couple weeks on digital, give the people that are taking the EC 271, 272 maybe a little bit of a head start, and if you're not taking that, maybe give you a little bit of a jump start also. So obviously digital, we're going to look at different number systems. So we normally are base 10 most of the time. I guess there's other bases, and the one we'll look at probably most predominantly in this area would be a binary or base 2. So base 2. We might talk about hexadecimal just a little bit in passing. You'll use that quite a bit if you do a lot of computer work, which is base 16. Most of our work, like I said, will be binary. That makes sense, either a 0 or a 1. When you start thinking about how to build things, you build them with switches. The switch is either off or the switch is on. Makes it a lot easier than trying to have a switch that has 10 different positions or something like that. So let's work our way through binary. If we take a 4-bit number, you might have something that looks like this: a 1 and a 0 and a 1 and a 0. And we'd call this the least significant bit, and this the most significant bit. And you could apply a lot of these to the base 10 system. If you go back and think about what was talked about when you first started learning the base 10 system in grade school or whatnot, there was the most significant digit and the least significant digit and things like that. So if we look at this, this would be the 1's places. This is then the 2's places. This is the 4's. And this is the 8's. So when we look at the number that I've written up there, 1010, that's actually what? 10? Is that right? Yeah, that's actually 10. Maybe, and a lot of times it's fairly easy to make those conversions. If someone gives you 10, it's pretty easy to make that conversion. Maybe we should put down a little procedure. Let's say that we wanted to make a conversion of 5. What would 5 look like? That's 5 base 10 to whatever it is in base 2. You might say, well, I can look at that with 1's and 2's and 4's. I think it probably looks like this: 0, 1, 0, 1. Is that right? Okay. Well, how could we get to that? How could we maybe get an algorithm to do that if you had something that was more complicated? And here's the process you go through. If you're reading through Shams, you're going to see something like this. You would take 5 and you would divide it by 2, which gives you 2. 2 goes in there, that would be 4, and then you'd have a remainder of 1, right? Remember when you first learned to do long division, instead of doing a decimal or a fraction, you talked about these remainders. So we'd have a remainder of 1. And what we're going to do is bring that over to the least significant. So we'll put that 1 right there. And then I'm going to take this 2 here and bring that down. Whoops, not that one, the other one. This is not that great of an example with that. There we go. This 2. Bring that down. So I would have 2 divided by 2 then, which gives me 1 with a remainder of 0. So I'm going to bring that down. And then I would have 1, so I bring this down, 1 divided by 2, which gives me 0 with a remainder of 1. So that's how I'd come up with that one. Of course, if you wanted to finish this up, then you would have 0 divided by 2 is equal to 0, and you'd get that leading on there. So if you needed a routine to get that, that's how you could do that on more complicated numbers. Most of the numbers we'll be looking at, you probably just do it by inspection. One that's probably a little more difficult is looking at a decimal. Let's look at that real quick, unless there's any questions. Okay. So let's say that we had something like this. Why don't we take an 8 0.125 in the base 10 system, and we're trying to convert it to something in the base 2 system. So the process through this, and again, Sham's outline does a good job of outlining this, I think. We take this 0.125, we're going to multiply now, because we're on the right-hand side of the decimal, by 2, which gives us 0.250. And then I take that 0.250, so 0.250, and I'm going to multiply that by 2, which gives me 0.50. And then I'm going to take that 0.5, and I'm going to multiply that by 2, which gives me 1, or 1.0. So what I do with this is this one I can bring over to here. So I'll have a decimal place, and then I'll have that one. Then this one I'm going to bring over to here. And finally, this one I bring over to there. So we'd have 0.001, which tends to make sense when we think about this as, what, an eighth, right? I think that should work. Questions of that? So that's how you make conversions on the both sides of the decimal point. Your author goes through a lot more examples. I'm not going to belabor it, but a lot of times probably you're going to grab your calculator and make the conversion, or the computer. This is how you'd write the algorithm to do that if you needed to. We might talk real quickly about hexadecimal numbers. Let's look at hexadecimal. We might call sometimes hex, which is, we said base 16. So you might wonder, well, what kind of symbols have they hid from me all these years? Well, not really. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we start with A and B and C and D and E and F gets us to 16. It's kind of interesting. We just write down 0 here to kind of take that for granted. For hundreds and thousands of years, 0 was not a really welcome concept. Because with 0, then you have to embrace infinity, and there were a lot of people died. They didn't want to think about 0, and they didn't want to think about infinity. So it's kind of interesting. We just write that down and take that as solid as anything else. But those are our hexadecimal characters. So I guess for completeness sake, let's build ourselves a little table here of, we'll say decimal or base 10. And then we'll have binary. And then we will have hexadecimal. So if I start out with 0, that's pretty easy. Binary, that's going to be 0. Hexadecimal, that's 0. Then 3, that would be in binary. Let's go with a 4-bit number, so maybe I should have said 0, 0, 0 here. So we would have, what, 0, 0, 1, 1. We take a 2 and a 1, we get a 3. This would be 3. If I look at 8, that's going to be, what, 1, 0, 0, 0. This is 8. If I look at 14, and sometimes in binary we might break this up and represent the 1 and the 4. I'll just say we're going to do it as a 4-bit. So we'll have 1, 1, 1, 0, I think. And that would be, where would it be in hex? So if we're over here, we would have, this is our 10, 11, 12, 13, 14, 15, right? So what would that be in hex? E? Okay. So if we have 23 then, let's try that. I'm going to need, what, 5 bits. So I'll have to go with a 16 and then a 4 and a 2 and a 1. So I've gone to a 5-bit number there. And how do I get that with hex? Well, just like I've taken a 16 and a 4, a 2, and a 1, I really need a, what, 16 and 7? So what's that going to be? 1 and a 7? So, about 29. So with a binary, a 5-bit number, take a 16 and an 8 and a 4 and a 1. And then what am I going to need here? I need 16 and what, 13? So, I'm just going from decimal to hex.
So is that on the both 1 and 2, is that I? 1.
Just 1. Questions with that? Yes? Because you've got, I mean, the, let's say if we go back over to, let's do 3, and let's think about it in terms of binary. I would take a 2, that's a 2, and a 1, right? Okay, so if I come back over here, this is representing what, 16, and then 7? A decimal is a 1. I'm not following that. Oh, if you had a decimal 1? A decimal 1 would just be 1. Well, 1 would be there. It would be in a different spot. Yeah.
So we can figure out the test estimate. Over 15, when you pass that number, you start over, and 0 is how to work within 0.
Right.
You start out with 1.
Yes. Just like you did with 2, you start over there. Once you go past 1 here, you have to move over.
So if you have something 132, you have 1.
More than 32, yeah. So, other questions? We're good on that? So, most of our work will really be in binary. I just threw hex in there because it seems like the right thing to do at this point. I guess this gives way to the expression. Maybe you've seen it on some T-shirts and whatnot. There are Is that right? Digital or binary, put whatever word you want in there. The average person reads that as 10 and goes, huh? If you know what you're doing, you read it as what? 2. Okay, so wear a T-shirt like that, you'll be guaranteed you won't get any dates. So. Okay, so any other questions? There's lots of other ways to represent things. Like a lot of times, like I mentioned, they will break this up and represent the 1 and the 4 separately. I'm not going to belabor that. You're going to spend a lot more time talking about this, but I just wanted to get a basic understanding here. Let's start to talk about some basic gates now that we're a little more comfortable dealing with ones and zeros. So basic logic gates. So we can think about things as switches, something being open or closed. The first one we'll look at is we'll talk about the AND gate. The AND gate, and if I need a symbol on the AND gate, it's going to look something like this. That would be a 2-input AND gate, might have an A input and a B input, and then it's got an output. So this is our in, and this is our out. And the way we can think about building this thing, if we wanted to, we could really look at this in a analog sense, since we've spent a lot of time in analog. We could have some source here, and we could have a couple of switches. We might say that this is the A switch, and then this would go to the B switch, and then we might have some way of indicating a condition, a light bulb, or something that we could turn on and off. And if I try and come up with a truth table on this, if I look at the condition of switch A and I look at the condition of switch B, where this is open, this is open, and open, and this is closed, and then closed, and open, and closed, and finally closed. Those are our 4 possible conditions, right? So then when we look at this light or this output Y, what are we going to have here? If they're both open, that is off or no. This would then be, if one is open and one is closed, what would we have? No. If this is closed and that one's open, no. It's only when they're both closed would we have a yes on the light, right? Well, we can take this over into what you probably would expect more in terms of a binary with our inputs, A and B, and we'd say that we'd have 0, 0, 1, 1, 0 indicating open, 1 indicating closed, and then we could have a 0, 1, 0, 1, and our output, our Y, our output, would be 0, 0, 0, 1. Okay? So I mean, I could have said, well, you use this thing and you get that truth table. But I wanted to try and put this into a circuit that you could actually go down to the lab and build. Are there practical uses for a circuit like this? Yeah. I mean, when we compare it to the OR, I don't want to spoil too many surprises, but I mean, with an OR here, we're going to have something that looks like this. And it's going to come up and it's going to have 2 switches that are in parallel rather than in series, running down to the light. Okay, let's keep this well segregated here. This is our OR. Okay. So some modern things that you might use. What if we had, let's say, your safety starting switches. If you have a car, if it's a manual transmission, before the engine will start, you have to turn the key on. So this might be our key, and this might be the transmission, the neutral safety switch, or the clutch pushed in switch. Would that be the way that you would want that? Yeah, because you want the transmission to be in neutral or the clutch to be pushed in, whatever transmission you have, and the key turned on. You wouldn't want this arrangement, would you? Where you could either start it in gear with the key, or you could start it without the key just by pushing in the clutch. That would be a wrong arrangement, wouldn't it? Okay, so some of these things you can think of as things that you've been around quite a while. When we start to look at having an alarm or something, we might have a switch at each window, okay, and do that. Or a safety loop on a furnace. Before your furnace can start up, We probably want to make sure that the draft inducer is working. We probably want to make sure that the temperature is not too high. We would have several checks, and all of those checks would have to be closed for that to work out, right? Okay. So logically speaking, I don't think this is too big of a deal. The Boolean expression for this is to say that we have A and B is equal to Y. So there's the symbol for and. And a lot of times we don't write that. We might just come up and say A and B is equal to Y. So we'll get kind of casual with that and not put that in there necessarily. So that would be our AND gate. Maybe we better talk a little bit when we bring up this term Boolean. Maybe we talk about some Boolean rules. Are there any questions before we move on to that? Let's try that. So Boolean rules or Boolean algebra with the AND. So if I take A and I AND it with a 0, what are we going to get? 0. Yeah, no matter what A is, if the other switch is open, then nothing's going to turn on. If I take A and I AND it with a 1, what will I get? Whatever A is, right? Did you talk about this stuff in discrete math? Okay, good. A ANDed with A gives me A, and A ANDed with not A, this is not A, which is the opposite of A. So if A is a high or A is 1, it'd be a 0. If A is 0, it would be a high. So if I AND it with that, I have to get 0, right? A few other things. If I want a 3 input, let's say that I want to take A, AND it with B, AND it with C to get my output. I could get a 3 input AND gate to actually make those like that. So you'd have A, B, and C, and then there's your output. Could you build it with 2 inputs? Sure. You could. We'll talk about how you can take gates and combine them. This is a fairly simple one. You take a 2 input like this and have your A and B, and then you would feed that along with this one into another one, and you'd get exactly the same thing. Okay. What would the truth table on either one of these be? It'd be kind of long, wouldn't it? I guess I can get through this. So let's see, 0, 0, 0, 0, 1, 1, 1, 1, and 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. The only way you're going to get an output is what?
Should be 8.
There should be 8. Do I not have 8? Okay. Yeah, this is the only one where I'm going to get a 1 out, right? The rest of them are all zeros. Okay. Questions of that? So that's the AND. We'll talk about how to make that from other things and take it and also turn it into other things. But let's look at the OR. So we'll have 6 here. So the OR gate. So with the OR gate, if I do this, and I kind of spoiled the surprise here, but I'll redo it. If I were to build this out of an analog circuit like we would be comfortable with in the past, I'd have something like this. I could say this was the A switch and the B switch. And we'd have something like that. If I look at the way this works, if either one of the switches is closed or both of them are closed, the light's going to light, isn't it? Okay. So what's our truth table going to look like? A and B, and I won't belabor the open and closed. I think you can probably make the extension here. So if I have 0, 0, 1, 1, 0, 1, 0, 1, we would have 0 and then 1 and then 1 and then 1. Okay. What this looks like in terms of a symbol is you'd have something usually as kind of a curved back, and then it'll look something kind of like this. You'd have A and B, those are your inputs, and your output is Y. Sometimes they'll draw it a little differently. Maybe they'll have this concave like that. I would take that as the same thing. Okay, those are really to be thought of as the same. What's your Boolean expression look like? A or B is equal to the output. So there's your symbol for or. And we tend not to omit that one. While we'll omit the and read it in context, we usually don't omit the ors. What might be a practical use for a circuit that looks like this? You ever driven in or ridden in a car, been around a car that has electric windows? For the passenger's window, there's usually a switch for the passenger, right? Okay. And who else usually has a switch for the passenger's window? The driver. Okay, so arrangement like that might work well for something like that, right? Either one of them. Okay. Now it's probably not how it's wired. It's probably a little more like a three-way switch in your house, but logically we would have the same thing. And you could think of this as also an alarm system, right? If you had a switch on the back door that got closed when the door opened or when the glass broke out of it, and a switch on the front door that got closed when it was disturbed, that would be our alarm system. We'd want it to go off if the back door opened and the front was okay, if the front door opened as the back was okay, or if they were both open simultaneously, we would hope it would go off, right? Okay, so we can start to think about that logically. If we look at our Boolean laws here, we're going to have A or 0 gives me what? Whatever A is. A or 1 is always going to give me 1. A or A will give me whatever A is. And finally, A or not A is always going to give me 1. Because I know one of those has to be a high.
Are we using A as, even if A was like an A naught, it would still be that same state?
Well, I mean, for instance, we could go through these. I mean, we could say that A is equal to 1 and go through this. And they would be just as valid if we were to then turn around and say, well, A is equal to 0. So I'm just using it as a variable. Other questions? We could do a 3-input gate. Those are fairly common. So we'd have A and B and C. And then we could build one out of 2-input gates. What would that look like? Something like this. And then that's going to feed with this into another OR. What's the truth table on the 3-input going to look like? So A, B, C, and their output Y. So 3-input OR gate. So 0, 0, 0, 0, 1, 1, 1, 1. So maybe I should say, what's the one case where you wouldn't have a high on the output? Yeah, this is the only one. The rest of them, if any of them are 1s or all of them are 1s, you're going to get a high, aren't you? So to some extent, it's the opposite of and, isn't it? I don't want to belabor that too much, but I think we also recognize this in popular culture. I mean, if I were to tell you to do something and I used an and descriptor versus an or descriptor, it could be a very different thing, right? Okay. So.
But you don't necessarily get the same result, but where are you saying that an OR gate and an AND gate?
An OR gate and an AND, or an OR gate and a NAND? I haven't got to NAND yet. Okay. So, yeah, the NAND special, that's universal. So, let's look at the NOT gate. So, the NOT gate, what we call the inverter. And it has a couple of different symbols. Sometimes it'll look like this, or another very valid symbol is it'll look like that. And this bubble, a lot of times they'll use that bubble to indicate that they've inverted something. So pretty common there. If I have an input of A and an output of Y, or input of A and an output of Y, your truth table for A and your output Y. And if you get to put in a 0, you get a 1 out. Put in a 1, you get a 0 out. Hopefully fairly straightforward. Your Boolean expression is that it inverts it. I guess the laws, what is the inverse of 0? Well, the easiest question of the day, 1, right? And the inverse of 1 is 0. And if I invert something twice, what do I get? Back to what I started with, right? So you put two inverters in series and you have not done a thing. Questions of that? So that's the NOT, the inverter. We'll move on. Someone asked about NAND. I guess it's time we look at that. We probably should have looked at it at the beginning, but that would be a little bit like learning to maybe run first, because that's just a special case of crawling. Let's look at this, the NAND gate. So with the NAND gate, what we do is we take an AND gate and we add to it an inverter like this, and that gets us, we use this enough that as a special symbol, the NAND. Okay, the NAND, N-A-N-D. So if I look at inputs A and B and output Y, you could say with A and B, so 0, 0, 1, 1, 0, 1, 0, 1. I'm going to have a, let's see, normally with an AND this would be low, but because I've inverted it, it should be a high. This would then be a high, a 1. This would be a high, and this would be a low 0, wouldn't it? Okay. Let's see, what's this going to look like from a Boolean expression? What's our AND? We would have A and B, and then I would invert that entire thing, and there's our output. Okay. If you've heard of De Morgan's theorem, we're going to get into those. I guess for now, suffice to say that this is not the same as inverting A and ANDing it with the inverse of B. That would be putting the inverters on the input. And we'll talk about what we get when we put the inverters on the input. So not the same as that. So we make the and then we invert it. So this is inverting it after we've made the and. The neat thing about the NAND is we'll find out it's the universal gate. The series that we're going to use, TTL, transistor logic, it's a 7400. I guess I better clean that up.
The one number you can't turn into.
What's that? Yeah. So 7400 series, and in fact the first chip in that series, 7400, is a NAND. You might think, well, wouldn't it be an AND? Well, no, AND is not as popular as a NAND, because if you had to spend some time on a deserted island and you wanted to start building stuff, if you could only pick one chip, it would be the NAND, because you can make every other chip from a NAND. Okay. So it's the universal one. We'll talk about how we could build those in a little bit. Well, if there's a NAND, there must be a NOR. So let's try that. A NOR. So what we're going to do there is we're going to take an OR and add to it an inverter. And we will get its own symbol like this. So there's our A, B, the Y out, and this is the symbol for a NOR gate. If I want a Boolean expression for this, I would have A or B, and then I invert that is equal to my output, and that again would not be the same as inverting them individually and doing the OR. What do you get when you have a truth table on this thing? Let's see, normally this would be with an OR, this would be the only one that is 0, but if I invert that, it should be the only one that I get with a 1, right? So I'm just taking the truth table for an OR and I'm inverting that. Okay. Questions so far? Yes?
Is the more than the one where you distribute the not and then change the
It essentially talks to us about how I really do relate that back to that. Yes, we'll show that. Okay. Well, let's see, we've done NORs. We've got a NAND and a NOR, not AND, not OR. So I guess it's the exclusive, or the next ones. Exclusive OR, which sometimes we call an XOR. Okay. And the symbol for this, we'll talk a little bit later about how we might build it. That's probably a little more complicated. Is I put a double back on this thing. So it's an OR with a double back. There's A, there's B, there's your output. Usually those go through. The Boolean expression for this is A, and then we had OR B, and if it's an XOR, we'll put this in a circle. Okay. And as we get ready to fill out the truth table, here's something that will help us fill out the truth table. Is a little expression. Any, but not all. Okay, so that's how that works. Any but not all. So I'd have 0, 0, 1, 1, 0, 1, 0, 1. So I would have 0 and 0 and 1, 1. Looks a lot like an OR, but when I get down here and they're both 1s, that would fail the not all, right? Any but not all. So that's our exclusive OR. And then while we're here, we'll have the exclusive NOR. Exclusive NOR. So we're going to invert what we just did. So this will look like this. And then we put an inverter bubble there. A, B, there's our output. The Boolean expression is exactly the same. We're going to take the OR, and then we make it an XOR, and then I have to invert the entire thing. So the Boolean, or the truth table, 0, 0, 1, 1, 0, 1, 0, 1. It's going to be the opposite of this one, isn't it? So it should be 1, 0, 0, 1. Questions with that? Yes? Probably because pen is kind of getting dull. Yeah. There. We're good. XNOR, yeah. Any other questions? Good? Okay, let's talk about how to build some of these things from the common gates. If you're going to use a lot of them, you're probably just going to buy a chip that has them, but if you want to just have one or two and you've got some chips laying around, you can make them up pretty easily. We said the universal was the NAND, so if I take that NAND, where I have something like that, and I add an inverter to that, so if I invert a NAND, what do I get? I get an AND. Okay. So now if I take a NOR, and I add an inverter to that, what do I get? An OR. And let's see, if I take an AND, and I add a inverter to that, we get a NAND. And if I take a OR, and I add an inverter to that, I get a NOT or NOR. Okay. So that's pretty easy. That's putting inverters on the output. Let's look at what happens when I put inverters on the input. So I take my inverters, take two of them now this time, and I add those to the input of a NOR. Okay. So that was a NOR, and that's going to then get us an AND. And if I take a couple of inverters here and add them to the front side of a NAND, so there's a NAND, we are getting an OR. Okay. So then if I take a couple of inverters, maybe I'll start over here. Oops. So if I take a couple inverters and put it on the front of a OR, we get a NAND. And if I take a couple of inverters and put those inverters on the front end of a AND, so this is an OR, This is an AND. We got a NOR. Then the million-dollar question here is, how can you get an inverter out of a NAND? So let's try this. Take this NAND. We have the two inputs here on our NAND. So this is our 7400. I'm not doing very well on that. There we go, 7400 NAND. Okay. And if I hook the two leads together, like that, I hook those together like that, let's see what I get out of this thing. So, if I look at, what do we have for our truth table for a NAND? We had let's see, for the NAND it would be the opposite, so I get a 1, 1, 1, 0, is that right? Okay, good. So this is the NAND. So if I select the two where they're the same, because when I hook these two together, the two inputs have to be the same, right? So we're going to be looking at either this one here or that one there. So if both of them are zeros, we get a 1 out. If both of them are 1s, we get a 0 out. So it looks like we have made what? An inverter. Okay. So now we know with a NAND we can make an inverter, and if we go back to these pictures here and start thinking about, okay, I can replace that with a NAND, I can replace that with a NAND, you can certainly see that you can build everything from a NAND. May not be the easiest way to do it, but you can. One thing that should probably, and I probably should have mentioned earlier, I talked about this connection here. In the past, when we had two wires that were crossing each other, we usually made a big deal about whether they were touching or whether they jumped over each other. We're going to have a lot of wires in these circuits that are crossing each other. So we're probably not going to necessarily do this that much. What we will do in our digital work is if they don't touch, it'll be like that. And if they do touch, we're going to put a dot there. Okay. So this is no contact, and this is contact. Where in the past we had this as no contact and this was contact. Okay. We don't want to have all those little jumps there, so this is probably a little more common in digital. Questions so far? Well, let's put some of these together in a circuit and see what we can come up with. So let me build this thing, some ands and nors. Okay, so let's say that we come across a circuit like that, and we'd like to try and figure out what it does, or at least how it behaves. So we might put some inputs into A and B. So let's say that I have A and B, those are our inputs, and we'll start out just like we normally do. And maybe I'll have some different outputs here. I might talk about this as maybe output 1, x1. Maybe I'll talk about that as output 2, x2. So let's talk a little bit about what we have there. I guess if I look at this, this would be whatever A is, that's just going to pass through. And then B, this is going to be not B, isn't it? Whereas when we get down here, what's this going to be? Not A, isn't it? Whereas this is just good old B, isn't it? Okay. So if I look at this then, I'm going to, if I go to AND A and a not B, so when I AND A and a not B, I should get 0 here, shouldn't I? Then if I AND this one, I should get 0. But if I AND this one, if I've inverted B, I'm ANDing a 1 and a 1, I should get a 1, shouldn't I? And of course, then this one would be back to 0. And likewise, if I go through and I talk about x2, what am I going to get with x2? This will be 0. Now this will be 1. This will be 0. And that will be 0. So what are we doing with x1 and x2? We're running those into an OR, aren't we? So if I look at an OR, we would have then for the output, when I OR those, I have a 0, I have a 1, I have a 1, and I have a 0. So what in the world is this thing if we wanted to give it a name? Yeah, exclusive OR, an XOR is how it's behaving. Questions with that? Well, let's try another one. So maybe we'll start this from a Boolean expression. We'll say that we have A and not B, or not A and B, or A and B is equal to output Y, which is a fine statement for our first go around. Probably going to be a lot more common to see this written A and not B, or not A and B, or A and B is equal to Y. Those would be the same statements. Like I said, a lot of times we omit that and in there. So could I build this thing? What are we going to be doing? It looks like we're doing some ANDing and some ORing, right? So it looks like I'm going to have 3 2-input AND gates. Okay, and those are going to be going into a OR. We'll just take a 3-input OR gate. You could make it for multiple 2-input OR gates. So it looks like we've got the output there, don't we? And if I start out with this one, A and not B, right? So there's A, that's going into there, and then I have B, and I better put an inverter in there, like that. So that takes care of that first term. And then I need to invert the second term, don't I? So I'll put an inverter here, and we'll come from there into that. And we just want plain old B there. And what's the last one? Just plain old A and B, right? Okay. So what's the truth table look like on this thing? So if A and B are both 0, what are we going to get? These are all going to be 0 at this point, aren't they? If A and B are 0, this would be 0 here, this would be 0 there, and that would be 0 there, wouldn't it? Because at no point are we inverting both of them. So that would be 0. But then if I get an A is 0 and B is 1, let's see, this is still going to be nothing here, right? But this one's kind of interesting. Now when I invert A, what do I get out of this thing? I get a 1 out of that, don't I? And what do I need for the OR? I only with one positive or 1 1 coming into the OR, with a high coming into the OR, I will get a high out of it, won't I? So I have a 1. And I could argue the exact same thing, but this time I could say it was up here, right? This time I'm getting a 0 out of this, but I'm getting a 1 out of that one. A 1 going in there will give me a 1 when I OR it. And finally, this last one, do I get a 1 out of anywhere? I'm not going to here. I'm going to get a 0 out of here. I'm going to get a 0 out of there. But here, if you take and you put a 1 in and you AND it with a 1, you're going to get a 1 out. So that will give you a 1. So how's that behaving? Looks like the hard way to build a NAND, doesn't it? Yeah. Well, I guess not a NAND. Let's see, a OR. Yeah, hard way to build a OR gate. Which brings us to a pretty good point. When we get to the next lecture, we've got a little more of this to do and whatnot, but we'll also start thinking about circuit simplification. How can I take something like this and try and make it simpler? Obviously, if this is an OR gate, we would like to replace it with this, wouldn't we? Less capital expense, less concerns with reliability, less power consumption. I mean, unless we're getting paid by the gate, there's really no disadvantage to that one, right? Okay. Sometimes you'd swear people are getting paid by the gate, but so we probably want some sort of method to go through and simplify this, and we'll look at kind of a painful method, Boolean algebra. We're not going to spend much time on that because there's a lot better, or at least a lot more fun method, Karnaugh Maps. Okay, and we'll spend a lot of time on Karnaugh Maps doing that reduction. It's kind of a fun graphical tool. It's fairly recent. I mean, Boolean algebra goes back hundreds of years. Karnaugh Map goes back about 75 years. So that's where we'll go as we start talking about circuit simplification and how we can make things a little more efficient. So that's what we'll do when we get together next.